Bismillahirrahmanirrahim. I am Dr. Amir Shah, lecturer in Department of Chemistry, Guwahati University of Science and Technology. Today, the topic of our discussion is chemical reactions of benzene. This is lecture number 20 from the course Organic Chemistry, second, Heaven Court Chem 322. The outline of our lecture will include introduction to the reaction of benzene, then followed by electrophilic aromatic substitution of benzene, where we will discuss halogenation reaction of benzene, nitration reaction of benzene, then sulfonation reactions, and Friedel-Crafts alkylation as well as acylation. And at the end we have written some references from which this lecture has been taken. So first we will come to the introduction. Actually, benzene carried out four types of chemical reaction. First one is the electrophilic substitution reaction. The second one is the addition, third one is the oxidation reaction, and fourth one is the Birch reduction and other type of reductions too. But here we will focus only on the electrophilic aromatic substitution reaction. The other type we will discuss in the coming lectures. So in electrophilic aromatic substitution reaction, as we have mentioned in the outlines, we will discuss halogenation, which include bromination, chlorination, iodination, fluorination, and along with that we will discuss nitration, sulfonation, alkylation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. But before discussing in detail, we should know the general mechanism of electrophilic aromatic substitution reaction. In electrophilic aromatic substitution reaction, as appear from its name, here substitution takes place. Substitution of what? The substitution of one electrophile by another electrophile, and it is take place in an aromatic compound benzene, so that is why it is called electrophilic aromatic substitution reaction. So what electrophile replace or substitute which one electrophile? Mostly the electrophile which is substituted is proton, and the incoming electrophile may be different. It may be halogen, it may be nitro group, it may be sulfonic group, or many other. So now how this reaction take place, it's mean what are the steps used for to carry out this reaction. The first step is the formation electrophile. First electrophile is from, electrophile is electron deficient species. It in search of electron efficient center. And second is the ring, which act as a nucleophile, can attack on the electrophile and form a sigma complex. And in the third step, the deprotonation of sigma complex take place in order to restore aromaticity, is shown here. In the first step, an electrophile is generated, and in the second step, this benzene ring is a nucleophile and attack on this electrophile, and is a result of which an intermediate is formed. This intermediate is called a sigma complex. And in the final step, proton transfer take place. It means deprotonation take place, and is a result of this deprotonation of sigma complex, aromaticity is again restored. You see here aromaticity has been lost. So in order to get this aromaticity, this proton is deprotonated and we get the aromatic character in a compound because aromaticity gave stability to a compound. First, we will discuss the bromination of benzene. Bromination of benzene means the replacement of hydrogen by bromine. How it happens? Mostly we take bromine in the presence of a Lewis base. Lewis base may be used as iron bromide or it may be used as aluminum bromide. Iron bromide can be formed by the reaction of iron with bromine to form iron bromide. So benzene is treated with bromine in the presence of a Lewis acid. The Lewis acid may be iron bromide or aluminum bromide, and is a result of which electrophilic substitution, it means bromination takes place. What is the mechanism for that? First is the formation of electrophile. Here this bromine, the iron bromide which acts as a Lewis base, the Lewis base is that one which accepts electron. So it takes electron from the bromine and form this complex. In some cases the electrophile is free. For example, in this case, if electrophile is free, then the electrophile will be in the form of A such plus if E Br4, negative charge will be appear on it. In some cases it is free as such, and in some cases it is in a complex form. This depends upon on the stability of electrophile. If the electrophile is stable, then it will exist in the free state. But if the electrophile is not stable, then it will be in the form of complex form. So what may be the state? Let we have treated benzene with the complex form of electrophile. Here benzene in the first step, which act is a nucleophile, attack on this electrophile, and when it attack, so what will happen? A sigma complex will form. A sigma complex first is a result, mostly in many books it has been mentioned that first what is formed, mostly a pi complex is formed where there is interaction between the pi cloud and that of the electrophile. This is electrophile Br positive, and again it is if Br 3. So such type of pi complex is formed, and after the formation of this pi complex, then it is changed into sigma complex. In sigma complex, what happen? A true bond is formed. This is only an interaction between the electronic cloud and the electrophile. Such as complex is called pi complex. This is called pi complex. But in case of sigma complex, here a true sigma bond is formed between the electrophile and that of the ring carbon, as a result of which a positive charge on the adjacent carbon. This positive charge may be appear is on this adjacent carbon, or it may be also appear on this adjacent carbon. This sigma complex which is formed, it is resonance stabilized. Electron are shifted here, so when the electron are shifted here, positive charge will be appear on this carbon, and similarly these electron can be shifted here and positive charge can be appear on that. And in the final step, this species which is formed during the first step can act as a base. It abstracts this hydrogen from the sigma complex. It means it deprotonates the sigma complex, is a result of which this bond is shifted here and aromaticity is retained, And along with this, some byproducts are also formed, which are iron bromide and HBr iron bromide, which was used as a catalyst, is obtained again, and HBr is eliminated during this chemical reaction. The second one is the chlorination. Just like bromine, chlorine is also added. Chlorine can also added to benzene in the presence of Lewis acid, for example aluminium chloride. In the presence of Lewis acid, aluminium chloride, chlorine substitute a hydrogen in itself added to one of the carbon, and we get a substituted benzene. Mechanism is the same as we have discussed in previous slide, that here the aluminium chloride, which is a Lewis base, it accepts this electron and form a electrophile, which is present in the complex form. In the polyester, again a pi complex is formed as we have discussed already, and then this pi complex is converted into sigma complex. As such, in pi complex there is only an interaction between the electronic cloud and that of the electrophile. In the polyester, then it is changed into a sigma complex, where there is a proper bond between the electrophile and one of the carbon of the ring, and on the adjacent carbon a positive charge is appear, and then the positive charge is not only limited to only one carbon atom, but it spread over the whole ring. The electron transfer here, this positive charge is transferred to this carbon, then these electrons are shifted here and the positive charge is shifted here. So a sigma complex, then it is deprotonated by this species which is formed during the first step. This species, it is a base because it abstracts a proton. By abstracting a proton from the sigma complex, the aromaticity is restored and we get a substituted product along with the catalyst that we have used in the form of aluminium chloride, and HCl is eliminated during this chemical reaction. Similarly, benzene can be also treated with iodine to get iodinations, but here the catalyst used is the copper chloride. How it is done? In the presence of iodine, it is in the presence of copper chloride, iodine is treated with benzene and hydrogen is replaced by iodine and we get iodobenzene. Similarly, fluorination is also take place, but chlorine is very reactive, so is a result of which polysubstitution or polyfluorination take place. It means we cannot stop this reaction to monosubstitute it as in case of iodine or bromine or chlorine, but many fluorination are possible. For example, if we show in that only we can get only this one, but along with this we can get the difluoro and along with the trifluoro and so many other, until all the hydrogen has been replaced. Why it is so? Because here the fluorine is more and more reactive, so mostly we ignore such reaction because it is very vigorous and very reactive and dangerous reaction, so we do not carry it. We do not mainly focus on the fluorination of benzene. The third one is the nitration of benzene. For the nitration of benzene, various type of mixtures used in order to carry out nitration of benzene. The common nitrating mixture used for the nitration of benzene is nitric acid and sulfuric acid. Beside this, many other nitrating mixture can be used, for example nitrogen pentoxide and so many other. What is the mechanism of this reaction? Actually here you can see that this is nitric acid and this is sulfuric acid. Here nitric acid is also an acid and sulfuric acid is also an acid, but here in this reaction one of them will act as a base and the other will act as acid. So here it has a lone pair of electron, it gave lone pair of electron, so it will act as a Lewis base here, and sulfuric acid will accept this lone pair of electron. It will accept, it will take this hydrogen, it will give this electron to the hydrogen, and it is a result of which we can get this species, and sulfonate bisulfate ion is eliminated. In the following step, the electron are shifted from here to this, and the water molecule is eliminated, and we get this nitronium ion, and this nitronium ion is free. It is not in complex form. It is stable, it can exist freely, so it can also be detected through spectroscopy too. And this species is electrophile because it is electron deficient species, so benzene can attack on this. Benzene here has a plenty of electron, it is a nucleophile in this step, and when it attack on it, first it form a 5 complex, and from the 5 complex then it is changed into what? From the 5 complex it is changed into sigma complex, as we have mentioned in the previous slide, that in the 5 complex only there is interaction between the cloud of electron of the aromatic ring and that of the electrophile, but in sigma complex there is a proper bond between the electrophile and one of the carbon of the ring. When a proper sigma bond is found between the ring and that of the electrophile, the positive charge appear on the adjacent carbon, and this positive charge is then spread over the whole ring through delocalization process. And in the final step, this hydrogen is abstracted. This hydrogen is abstracted by a Lewis base, and by the abstraction of this sigma bond is shifted here and the aromaticity is restored. The nitration of benzene is very important reaction, and it is used for the formation of various type of important compound. For example, if a nitration is done, and after nitration, if it is treated with zinc and HCl, this nitro group is reduced into NH2 group, and you know aniline is very important reagent, and it is used for the synthesis of many type of compound that we will discuss in the coming lecture. The other topic is the sulfonation of benzene. Sulfonation can be done with the help of fuming sulfuric acid or very strong sulfuric acid. Fuming sulfuric acid is that sulfuric acid in which sulfur trioxide is present, and strong sulfuric acid are it is also called strong sulfuric acid. It is also occurred through concentrated sulfuric acid too. So what happened here? Here the hydrogen is replaced by a sulfonic group, so that is why it is called sulfonation. The mechanism of this reaction is shown here, that here sulfur trioxide is present. The sulfur trioxide is present, so here is the positive center in the sulfur trioxide. Actually the valency of the sulfur is looking satisfied because sulfur has 6 electron in their outer motion, and all the 6 so it is valency it is satisfied, but still it is electron deficient. How we can know that it is electron deficient? We know that in case of sulfur, The pi bond, the p orbital which is overlapped with the p orbital of oxygen to form a pi bond, the overlap is not maximum overlapping. Why the overlapping is not maximum? Because here these p orbital are unmatched. If they are unmatched, the overlap will be not maximum. So that is why the valency of sulfur is not fully satisfied. Sulfur will have still positive charge in oxygen will have sulfur will have still partial positive charge, oxygen will have partial negative, all oxygen will have partial negative charge. So it means there is an electrophilic center, and the benzene has a plenty of electrons, so they can act as an nucleophile. So this pi electron first form a pi complex, and after the formation of a pi complex, this is only pi complex is formed only by the interaction of electronic cloud with electrophile. There is no proper interaction, but only a type of intermolecular interaction. Intramolecular forces are there because it is negative center and that one is the positive center. So an interaction, intermolecular interaction. It is not intramolecular, but it is inter one. And then it is what happened here, then a sigma complex is formed. A sigma complex is that one which is there is a proper sigma bond between the carbon of the ring and that of the electrophile. And when this sigma bond is formed between the electrophile and that of the ring, on the adjacent carbon positive charge will be appear, and this positive charge is further delocalized over the whole ring through resonance. And in the final step, the hydrogen is taken out by this sulfonate group. Here this species is a big base because it abstracts a proton, and by abstraction of this proton, this sigma bond will be shifted here. By shifting of this, aromaticity will be restored. Still it has negative charge, so it will abstract hydrogen from the sulfuric acid and will form a sulfonic group, and we will get benzene sulfuric acid. This sulfonation is a reversible reaction. It is a thermodynamic phenomenon. It is not a kinetic one. Here, when we treat concentrated or heming sulfuric acid with benzene, so benzene sulfonic acid is obtained. But when this benzene sulfonic acid is diluted with sulfuric acid, we can get benzene again. So sulfonic group is very important from the synthetic point of view, where it is used for the protection and deprotection of a certain position in the rings. The other topic is the Friedel-Kopp alkylation. And Friedel-Kopp alkylation, where alkyl group is introduced. This reaction was introduced by Charles Friedel and James Kraft, and they have also got Nobel Prize through this reaction, and they have discovered this reaction in 1877. What happened in this reaction? Here installation of alkyl group takes place, is shown here. Alkyl group installed here. Different type of reagent are used for the alkylation. They may be alkyl halide, they may be alkenes, they may be alcohol, but the most commonly used reagent is the alkyl halide, which react with benzene in the presence of a Lewis base aluminum chloride, where hydrogen is replaced by this alkyl group, and we get alkylated benzene. Mechanistically, it has been shown here that aluminum chloride acts as a Lewis base. It takes electron from this chlorine and from this complex, and after the formation of this complex, electrons are shifted here, and we get a cation which acts as an electrophile. This electrophile may be free or may be in combined state. It depends upon its stability. Mostly if the alkyl group is if the cation is tertiary, so it will be more stable. If it is second compared to secondary, and secondary will be more stable compared to the primary carbocation. Primary carbocation are more stable compared to methyl carbocation. After the formation of alkyl carbocation, it is attacked by the benzene, where benzene acts as an nucleophile. In this species, it is an electrophile, and by attacking of this, 5 complexes form, and then from 5 complex it is converted into sigma complex, where in sigma complex a proper sigma bond is formed, and along with it positive charge appear on the adjacent carbon, which is delocalized over the ring. It is not limited only to one carbon, but it spread over the whole ring, and that's why the sigma complex is stable 1. And then in the final step, hydrogen is abstracted from the sigma complex, where the sigma bond is transferred to the ring to restore aromaticity, and as a result we get the alkylated product, and along with that aluminum chloride, which was used as a catalyst, is eliminated, and HCl is also eliminated during this chemical reaction. This chemical reaction, it means the Friedel-Koch alkylation is very important. It helpful in ring closure reaction, which has a hallusion, but only it is possible. It means the ring closure are possible when the hallusion or other living group present at a proper position. For example, it has been shown here. Here hallusion is present, but this hallusion is present at a proper position, so in that case ring closure is possible. Through which mechanism? Through which process? By Friedel-Koch alkylation process, where aluminum chloride it relieves base, it abstracts this chlorine and form aluminum tetrachloride. Positive charge will be appear on it, and then positive charge is attacked by the benzene ring, and then hydrogen is abstracted, and in the final we get this ring. And similarly, other substituted ring closure is also possible. For example, in this case, first there are 2 Friedel-Koch alkylation. First, it will attack on this position where chlorine will be eliminated, and after attacking of the formation of bond with this position, then the benzene ring will attack at this position and will also eliminate chlorine, and is a result of which this compound is obtained in the presence of Lewis base. But still this reaction has some limitations too. Number first is it causes polyalkylation. For example, if we carried out this reaction, so it will not only limit to monoalkylation or monomethylation, but cause methyl group further activate the ring. So if there are methyl group are present, so it will further attack on the ring, and instead of mono methyl or instead of toluene we will get diurine. Similarly, a rearrangement is also possible. For example, if we want to add N-propyl group to the ring, so this formation of this compound is not possible. It is possible, but it will form in a very minor amount. But the major product will be the rearranged product. The reason is that because when alkyl group, when the halide group is eliminated and positive charge appear on that, so that one is the primary. But there is a possibility of the formation of the secondary carbocation. So it will rearrange when the positive charge appear on it. So then the benzene ring will attack at this position, and that gas we will get the rearranged product, not the product, not the N-propyl product, but we will get isopropyl product. The isopropyl product is the rearranged product. The third one is that the carbon which is connected with the halogen, must be sp3. This carbon should be sp3. If it is sp2 carbon or if it is sp carbon, then alkylation is not possible, because here you see that all the conditions are okay, but only one problem here, that chlorine is bonded with a carbon which is not sp3 but it is sp2 carbon, so no reaction is possible in that case. Same is the case here. All the conditions are okay, benzene is present, Lewis base is present, but the chlorine here bonded with sp2 carbon, not with sp3 carbon, so no reaction will occur. Certain group, for example nitro group, are incompatible with the Friedel-Crafts alkylation reaction. For example, if we want to do this reaction, so the benzene ring has NO2 group, so it is not not compatible with this reaction, so alkylation is not possible for that reaction, because NO2 drag electron toward itself, it make this ring electron deficient, and this electrophile which is coming here is also electron deficient, so here alkylation will be not possible. The last topic is the Friedel-Crafts acylation, where in the Friedel-Crafts acylation, acyl group, SL group, it can be pronounced as acyl or SL group, where SL group is installed over the ring in case of Friedel-Crafts alkylation, where the various type of reagent used for acylation of benzene, maybe acid chloride, maybe acid anhydride, and many other, in the presence of Lewis base. Mechanistically, it has been shown here that one of the acyl halide is treated with the aluminium chloride to form this complex, and then the electron is transferred here, and we will get an electrophile. Then this acyl group is attacked by the benzene, which acts as an nucleophile, and this group acts as an electrophile to form a pi complex, and then the pi complex is converted into sigma complex. In the sigma complex, there is a proper sigma bond between the electrophile in the benzene ring, the carbon of the benzene ring, and along with it positive charge is formed on the adjacent carbon. Positive charge is delocalized, and in the last step the hydrogen is abstracted from the sigma complex, and the sigma bond is shifted towards the ring to restore aromaticity, and we get acyl substituted product as a result of this reaction. Now, what is the difference between alkylation and acylation reaction? Mostly both of them require Lewis base, which is aluminium chloride, but for acylation reaction, the amount of Lewis acid is more comparatively than alkylation. Why it is so? This is because aluminium chloride is not only used for generating electrophile in case of acylation, but it is also form a complex with the acyl group of the benzene ring. So that's why the Lewis base used for acylation is a little bit higher than that of alkylation. The second one is that if we get, as a result of alkylation, we will get alkylated product, and as a result of acylation, we will get acylated product. The isolation of acylated product is easy compared to that of alkylated. Why? Because it deactivates the ring for further attack. But in that case, it activates the ring for further attack. So we cannot get isolated monosubstituted alkylated product, because it activates the ring for further attack, so polyalkylation will take place here. And the other one is that through acylation we can get inalkylated product, as we have discussed in the previous section that inalkylated product was not possible through alkylation, where we get iso in branch, not in alkyl, but the branch type of alkyl group were added to the ring. But here we can get inalkylated product. First this acylation takes place, and then this CO group, keto group, is reduced to CH2, and as a result of which we can get a long chain alkylated product, which is possible only through acylation reaction. These are the references which I have taken this lecture from these books, and if you have any problem you can ask me through WhatsApp, or you can call me directly. And thank you for watching this video.